Okay, so welcome to the today's session. I'm going to discuss about introduction to VLSI design flow. So this is the first lecture in modeling and design with HDLs. Okay, uh, yeah. Actually, we did not focus mainly most concepts in the VLSI design flow, but whatever essential that we need to talk about. But it is required that everyone should know what is there in the VLSI design flow, right? Okay. Okay, this is the lecture plan they have scheduled for this today's session. The first one is overview of VLSI design flow. The second one is introduction to integrated circuits. The third one is figure of merits. Okay. Now look at the overflow of VLSI design flow. Overview of VLSI design flow. What is VLSI design flow? VLSI stands for very large scale integrated circuit integration, we can call it as. The design flow is the structural process. Please look at this one. It is a structural process, structured process. That means that it involves the number of steps in it. So to design the integrated circuit or an IC or a chip. It involves transforming an idea into a chip. It must be ready for manufacturing. Okay. It's all about translation from idea to the chip. In order to make any kind of chip, we start with some kind of idea. From there, the end product should be an integrated circuit or an IC or a chip. Okay. Look at this one, an idea. Okay, what is that an idea? For example, if you want to make an IC having, or it has to perform some kind of operations. For example, some kind of inputs here and some kind of outputs that we want to provide for this IC. So initially we have realized that, okay, for example, 3 inputs I'm giving and it should produce three outputs, right? This is some kind of functionality. Um, for example, multiplication, or for example, division, for example, whatever it may be. We focus mainly on the digital applications only. We want to realize this on IC because we have some kind of idea. The idea is that it has to perform some kind of task, okay, by applying some kind of input signals. Then it must be translated to an IC or a chip, whatever we have intended for, okay, whatever we have intended for. Okay, the same idea is implemented or realized in the form of a chip. In the form of a chip. Agreed? But this translation is not a single step process. Okay, it has multiple steps involved in it. Let us look at what are those things. We are going to see the essential steps in VLSI design flow, right? Okay, that means we started from idea and we want to translate into a chip. What are the essential steps that are involved in it. The first one is RTL design. Creating an RTL design is the first essential step. This is also called as pre-RTL flow. What we can call it as pre-RTL flow. Definitely from idea to RTL, there is some kind of steps involved in it. We are going to see that one, but this is called pre-RTL flow. That means whatever an idea we have here, that must be implemented, that must be written in the form of RTL code. RTL stands for Register Transfer Levels. It's simply an RTL code. The next one is RTL to GDS flow. Okay, this is called RTL to GDS flow, or normally this is also called as physical design. Normally we can call it as physical design. Okay, that means we are whatever the RTL code is there, that must be converted into a layer format. Okay, the layout design that we have to do with the help of different kind of masks, right? This is called GDS RTL to GDS flow. Now the later what we are going to see, we use the next step is that GDS to chip design. This is called post GDS flow. What we can call it as post GDS. Normally called as a graphic design system. That means whatever the layer information is there, that layer information we are writing in the form of a file. The extension of the file is GDS2. That is required to create or to realize an IC or a chip, right? So that means this flow is broadly divided into two parts. What are those? The thing we can call it as VLSI design flow from starting to the creating the GDS. Okay. The second one is the fabrication. Okay. Therefore, the entire flow is divided into two parts. One is the basic VLSI design flow. The second part is called fabrication. Let us see the individual steps. What is an pre-RTL flow? What is there in the pre-RTL flow? What is there in the RTL to GDS flow? What is there in the fabrication? Step by step. Let's talk about pre-RTL flow. As we know that from idea to RTL code. Okay. RTL code, actually, we focus mainly on this particular area, of course, because our course is completely relevant to creating an RTL code. Okay. Our course is all about creating an RTL flow. RTL code. So without RTL code, okay, you are not able to create any kind of IC. Okay. So therefore, it is very, very essential step for any IC fabrication, for any IC design. Okay. Therefore, in order to create an RTL flow, we are going to use hardware description languages, HDLs that we use. Okay. So how we can create an RTL code with the help of HDLs? What is an RTL? How we are writing this one with the HDL code? All those things we will see in the coming classes. For the time being, it's simply a programming language by which we are able to realize our idea, whatever idea we have. Okay, so usually we are going to use Verilog or VHDL or system Verilog. Nowadays, the people are talking about the system Verilog. Okay, so but if our syllabus is only restricted to the Verilog programming only. Okay, but we'll talk about the system Verilog for the designing also. Please see in this classes. Okay, yeah. So we are going to talk about the pre-RTL flow. So how we can create an RTL, that's the question here, based on the idea. Okay. So here we can see it involves two essential steps. One is called architectural design. The second one is called behavioral synthesis. What does that mean? So architectural design engineers are responsible to create an architecture of your chip. Whatever idea that we have, for example, if you want to create, for example, CPU, for example, central processing unit. Okay, what it will be there in that one? There is a arithmetic unit, logical unit. There will be a memory block, for example, some small memory block. Like this, we will have a different kind of modules or different kind of building blocks that are required to implement an idea. Okay, therefore the basic building blocks will be created by the architecture engineer, chip architect. So specific senior leads will take the responsibility how idea consisting of different basic building blocks in it, right? So they will create, they will use the different kind of blocks and then how they can interconnect so that they can perform some kind of task based on our idea, right? The next one is called behavioral synthesis. The behavioral synthesis will convert the functional specifications of architectural design, which are written in high-level abstractions. Generally, what we can see, as I mentioned that, for example, this is what an idea, for example, some kind of idea that we have here. For example, the input, different kind of inputs, different kind of outputs. What the architect will do, he will create some blocks to realize this particular idea. Okay, to create the blocks in it. Okay, and each and every block and overall the chip is written generally with the help of C programming or C++. Most preferably people will use the system C, especially when we talk about the hardware designs. Okay, so they will write the blocks behavior with the help of the programming languages. Now, what the behavioral synthesis will do, it will convert the the blocks the blocks that are there in an idea or maybe whatever the expected chip that is there, that will be written in the C language or maybe some other programming language that will convert into a RTL code. It is an automatic process. Okay, that means the design will be available in the form of a system C or maybe a C or C++. We have to give that code to the behavioral synthesis tools that are available. Okay, for example, high level synthesis. From Xilinx, we can use HLS. So the HLS is a tool that they are going to use to convert the high level abstraction into RTL code. It is automatic process. As I mentioned that not only the Xilinx, but different tools that are available, they can convert that one. Or otherwise, we can start the building blocks. We can write directly the RTL code. It is also possible. For example, this code generally they will write it in C or C++ or maybe some any other language they will use. But you can start directly from writing the RTL code. Manual is also possible. Is that clear? What is the behavioral synthesis and the architectural design? So this is called the pre-RTL flow. These are the basic steps that are there. Of course, there is iterative process actually it is, but we are not going to focus mainly on that one. We focus mainly on what are the different steps that are there. Right. Next, we are going to talk about RTL to GDS flow. This is also called physical design. We start from RTL code, okay, and then we can end with the GDS, graphic design system file generation, exclusive the layout formation. Now let us see what are the different steps involved in it. These are the basic and essential steps that they're in the RTL to GDS flow. The first one is called logic synthesis. The second one is called floor plan, place and route. Okay, so our intention is to create RTL code, convert the RTL code into a layout in this particular process. Okay, let us see what are the different steps here we can observe. These are, as I mentioned, there is a major steps, right? In addition to these steps, another important step is clock tree synthesis. Of course, it's a very, very essential step for any IC design. That is called clock tree synthesis. And always we always we do this kind of step that is called functional verification and timing analysis. Whenever you do some kind of change in the RTL code, whenever some kind of modification in the placement and floor planning and routing, definitely we have to perform functional verification and timing analysis. Okay, let's see one by one what the logic synthesis means, what is meaning of the floor plan, placing and routing and RTL, clock tree synthesis and functional verification and timing analysis, step by step. So let us talk about the functional verification. Okay, somehow we have created, idea is written in the form of RTL code. How can you say that that's correct? Okay, so that must be corrected, or that must, whatever the RTL code that we have written, that must be verified with the help of simulation tools. Okay, with the help of the simulation, we are able to verify the correctness of our RTL code. Okay, whether it is behaving as we have expected, right? So this step is always we can perform. Whatever, whenever we do some kind of modification, some other steps, whatever we have seen, always functional verification is very important. Okay, so from idea into RTL code, from RTL code to the layout, okay, layout to some other steps that are there, definitely we have to perform the functional verification, correctness of the functionality. For example, addition that we are writing. When you give the some kind of A and B and C, whether we are getting the sum and carry properly or not, we need to verify. Not only this one, code coverage concept is also there, but we are not going to talk about right now at this stage. There is a code coverage. Okay. Now we see the next step is logic synthesis. What do you mean by a logic synthesis? It translates the RTL code into a gate level representation. It's a gate level representation. Whatever RTL code that is there, RTL code is translated into gate level netlist. It's a pure gates, the implemented gates. Okay, so that means we take some technology file and the logic synthesis tool will take the technology library gates and create the pure gate level netlist. So generally the gate level netlist is actually the Verilog program. So for example, you are using the VHDL program for the design, for modeling of your hardware. What is the ultimate result from the logic synthesis? It's simply a Verilog code. If you give a Verilog, it will give the Verilog gate level netlist. Okay, for example, you write the Verilog code in behavioral modeling, for example. Last time we have seen, right? That will be converted into, again, the gate level netlist of the Verilog. Okay. But if you're using the VHDL, definitely the outcome will be a Verilog only. If you give the system Verilog, again, that will be converted into a Verilog gate level netlist. Am I right? So that is what the responsibility of the logic synthesis, converting the RTL code into gate level netlist, because the gates or the cells that are available in the standard cells. Okay, we'll talk about that word standard cells a little bit later, but this is simply a translation. The next one is design for test, DFT. Okay, so for example, you create a chip, for example, and during the design, during the fabrication, something went wrong. Okay, what we have to do? We have to test that particular IC after the fabrication. But it's very, very difficult doing that testing after the fabrication. We are going to provide some additional provision in the design phase itself that allows us to test the IC very comfortably. Okay, we did not focus, we did not worried about how we can test the IC after the fabrication. This provision will help us very easy to test the IC. Okay, so that is what the design for testing. During the design phase, we perform this kind of thing. Okay, once you create the logic synthesis, so logic synthesis, after that we insert some kind of scan cells within that particular gate level netlist, and we will perform another. We'll perform the logic synthesis for that again. The next one is floor planning. Okay, so the design is laid out on a physical grid. For example, in this floor plan, what we can see, according to the RTL code, okay, what are the different blocks that are there? Okay, all these blocks, that means what kind of area of the chip that we need to have. Okay, and what are the different blocks that are there in the code? All those things will be fixed in the floor planning phase. It is not actually placing up the standard cells here. It's not all about whatever exactly the things that are fixing here, but what are the essential blocks that are there? The blocks will be placed in the floor planning. Okay, you will see this kind of things while you are performing the VLSI design laboratory, more specifically. But it is simply creating a chip. What is its height? What is its width? Okay, from the RTL code. And what are the different basic blocks that we are using? Some blocks that we have to use it. How we can fix those blocks and create the grids for that particular. Okay, that information will be available in the floor planning. The chip related dimensions and then building blocks, whatever the building blocks that are there in the code, that will be fixed in the floor planning. Okay, the next one is called the planning. Placement is the next step. It is actually the exact placement of the cells. Okay, okay, for example, you are using the in RTL code, you're using, for example, AND gate and G1 sub example Y A comma B that we have used in RTL code. So in the technology library, what we can see, there is an AND gate in it, right? It will choose an AND gate, right? So therefore, it is a technology dependent AND gate. It is a technology dependent AND gate. So this AND gate have a, this we can call it as a standard cell. What we can call it as standard cell. So this standard cell we will place in a IC. Okay, in the previous floor planning stage, we have we can see there's a different kind of grids, right? So we can exactly take that particular gate as a standard cell and place it in a grid. Wherever it is possible, it will be placed in that one. Okay, that is the responsibility of the placement tool. Majority of the things are automatic. Just we have to give some kind of instructions, automatically the tool will perform this kind of thing. We cannot do it manually, placing of the cells. Is this point is clear? Yes. The next step is clock tree synthesis. Okay, it's a very, very essential step normally we use, because in our design we use the flip-flops, right? We are not going to concentrate only on the combinational blocks. We are going to use the sequential blocks as well. That means it involves the flip-flops, right? For example, you take one chip here, one flip-flop is available here, one flip-flop, another flip-flop is available here. So there is a common clock is available, right? Our intention is that this clock must go to this flip-flop and this flop at the same time. It has to go to these two flip-flops at the same time. So it is possible only with the help of clock tree synthesis. Okay. So therefore, with the help of the clock tree synthesis, we are able to provide the clock synchronously with all the flip-flops. Okay. That is what our intention is. Okay. So it will be taking responsibility of the clock tree synthesis mechanism. It will provide the clock to reach each and every flip-flop at the same time. Okay. Right. Next one is routing. Once we have performed the floor planning, once we have performed the placement, once we have performed the clock tree synthesis, then we'll go for a routing. Okay. So that means that it is providing the interconnections between the different standard cells. As simple as that. Okay. The different approaches that are there: global routing, detailed routing, child routing. So these things will come under the routing concept. Routing concept is just provide the interconnections among the standard cells. Okay. Next, timing analysis. Okay, without performing the timing analysis, we never release our chip, or we cannot say that our design is complete. Okay, so that means uh, whatever the target, the delay of the IC, okay, that must meet in this particular analysis. So in this particular analysis, we are able to say that whether the timing, the delay is properly maintained or not can be checked. Usually we use the slack is the one mechanism by which we are able to say whether we are attaining the signals at the right time or not. We can verify with the help of the slack. Okay, positive slack is required. There should not be any kind of negative slack in this design, right? We talk about more on the slack and related things we will see in the coming classes. Okay, of course, I'm not going to deal this kind of thing, but when time comes, I will discuss that point later. Okay, here we can see this is called, for this purpose, we are going to use the static timing analysis is the concept that we have to learn. Okay, so the static timing analysis is helpful for us, right? So the next one is physical verification. Okay, next, once we have created the chip, it is meeting all the timing constraints and the functional verification. It's very important that it will be converted into a layout, where then we have to see that design rule check must be verified. Okay, so because our design must be converted into a layout, right? Whenever you are creating a layout, definitely we have to check for design rules. Okay, DRC we normally call it as. Okay, that means one layer is how much distance from two layers apart. What is the width of this one? What is the length of this one? Whether we are meeting all the conditions or not, there is a rule file is available. With the help of the rule file, whatever the layout that we draw or the tool that is drawn, that will be verified. Okay, and not only that one, it will also check the LBS, layout versus schematic. Okay, so we say that the schematic of the chip is actually having the 3 inputs and the 3 outputs. Once it is translated into a layout, for example, it is having only 3 inputs and only 2 outputs, for example. It's a mismatch, right? That will also must be checked. Okay, so DRC and LVS is used for physical verification. Okay, the last step is in this particular one is tape out or GDS2 file creation. It is actually a file extension. GDS is actually a file extension. Like for example, doc is the one extension. Like you see the text is one extension. Like this, we have a .gds is one extension. What is this file consisting of? It consisting of the layer information. Okay, generally graphically we can see the chip layout, right? But that cannot be the way that we can give the information to the layout engineers, sorry, fabrication engineers. We have to give in the form of a file. Okay, yes. So therefore, finally, we have to tape out with the help of GDS file, and this file has to give it to the fabrication engineer. So all these things will come under the VLSI design flow, starting from idea to the GDS2. Right. What is the next step? Fabrication. From there, we are going to talk about the fabrication. We see the fabrication from this. Okay. So this is called post GDS flow, right? Okay. So these are the essential steps that we can see in the GDS, sorry, fabrication. Okay. What is the first step? Photolithography, etching, doping, deposition, chemical mechanical planar, CMP, and then metallization. Okay, so these are the majority of the fabrication steps. Of course, consisting of many things that are there, and repeated steps also will be there in it. Okay, all the time we perform the photolithography, all the time we perform the etching, all the time we perform the doping. This process is a repeated process actually. But what is the photolithography? Photolithography means creating a mask. Okay, creating a mask for this one. Okay, so it involves the photoresist material deposition, mask definition, and UV radiation or some kind of radiation. So by using this one, we are able to create a patterns on the chip. If you take a silicon wafer, okay, so we take a wafer. Okay, in this wafer, what we are going to do, if you want to create some kind of pattern, for example, A is the pattern that we are going to create, for example, some like this is the one pattern that we want to create on a wafer, silicon wafer. How do we do this one? With the help of photolithography. So create a patterns on a wafer. We are going to use the technique called photolithography. Okay, you have a VLSI technology subject is there, right? Course is there. No, you will learn more about the photolithography there. Etching is removes the material from the selected area. Unwanted materials you can remove from the wafer with the help of etching process. If you want to create, for example, source and drain, for example, this is called doping, right? For example, P plus diffusions. If you want to use, I'm going to go for doping concept. Next one is deposition. Okay, you can create some, for example, gate oxide on top of it. It is called deposition. So create a layer on another layer. That is called deposition. Diffusion means inside of the another material, penetrating or maybe deposition. Both things we can call it as. And planarization means that polishing. Actually, once you create some kind of things, we have to polish that particular one. Finally, metallization is there. That means provide the metal connects from one device to another device. If you want to create another device here, if you want to provide the interconnection between them, then we are going to use metals here. for example, metals. Please remember that the fabrication is actually completely automated process. Okay, completely automated process, highly automated. And we are going to use the, you know, we are going to use the very clean room that we have to use. That is called clean room environment is very, very important. Okay, it should avoid the contamination because the chip size is the transistor size that we are creating an IC is very, very narrow, nanometer scale that we create, right? Okay, our age is actually, people will say that a few angstroms, right? Sorry, few microns. But we are talking about the nanometer scale devices. That's the reason why the clean room is very essential. Okay, it can take few weeks to complete all the steps of the single wafer, but thousands of chips are produced simultaneously. Okay, so that means it is not an easy task that we can create an IC as simple as that. Okay, it involves uh, the large number of steps to create a simple IC. Okay, so that's what we are going to see today, and the next class we'll see some other concepts. Integrated circuit approach we will see in the next class, right? So let me conclude this one. So VLSI design flow will start with the from idea or a specification to the chip design. Okay, the major steps that we have seen is idea to RTL, RTL to GDS, GDS to chip design. Okay, so therefore this flow is broadly classified into two categories. One is called basic VLSI design flow. That's the next one is called fabrication. Okay, each and every step, what are the things that are there, we have seen, right? This is a basic overview. Actually, I'm not going to give you the detailed discussion of each and everything, but it's not the scope of our course also. Okay, we focus mainly on the RTL coding. You should know why RTL is required, RTL coding is required, what is the purpose. Okay, so in the coming classes we'll see what are the different type of ICs that are there. Okay, and what is the importance of the HDL, why we need to write the things in HDL only. That things we will see in the next class. We stop it here today. Okay. So the next class I'm going